Since the summer is so short, I jumped into chemical properties right from the get-go. And so we were talking about, over the summer, we're talking about burning, combustion, for example. So, for example, if you burn like methane gas, you're supposed to form CO2 in water. Right, but if there's not enough oxygen, you're going to have something incomplete combustion. Incomplete combustion, you can form soot, which is carbon, and carbon monoxide, which we didn't allow with the yellow flame. But what if you add more oxygen? If you add more oxygen, can you form carbon trioxide? Or carbon, CO3? Or what comes after tri? You know what? 3 is tri. 4 is... Terra's close. 4 is tetra. So can you form carbon tetroxide, or carbon pentoxide, or carbon hexoxide, or heptoxide, or octoxide, or nonoxide, or decoxide? Are those possible? Why stop at CO2? If we're trying to completely combust it, shouldn't we go to CO3 or CO4 or higher even? CO5? Why do we stop there? Well, one thing that people do is they just memorize it. So you could just go ahead and memorize it. Well, carbon-containing compounds can burn to carbon, soot, carbon monoxide, and carbon dioxide, right? And then that's it. That's just memorization. But over the summer, I wanted to step ahead, and get people thinking, And so over the summer, I talked about things like this. Early on, we're going to talk about this, but later. And so early on, I started introducing, the patterns of reactivity. And talking about the patterns of reactivity, like some of these questions might not make a whole lot of sense to you. For example, this one. Number 20. You look at number 20. Carbon can lose a max of 4 or gain a max of 2 electrons. True or false? Well, actually, this is false, but we talked about why that is, and then in that context, we talked about this. We could easily figure out what is going to form based on this pattern. Where did this pattern come from? This pattern came from the periodic table, which is there. And so, based on the position in the periodic table, we could figure things out. And so, I started talking about chemical reactions early on because that usually is a struggle. For students to grasp, so a little bit more time, it's always helpful. And so week 1, I got into it. For our class, I don't need to get into it so early. We'll just wait. And so lithium burning and nitrogen is the same type of thing. Same type of deal as number 20. So when I see number 20, number 29, number 47 are all related questions. And so if you couldn't answer those, that's fine. Don't worry about that because we're going to get to those later. What were the other questions? Was that it, just 47?
It was the ones after it as well, but I don't know if I didn't see the answers to those.
Well, let me tell you. Let me give you a hint for 48. 48. Take a look at your notes because I think I did that one on the board. Minus, what, does anybody even remember what the temperature is? Minus 40 is the correct temperature. Good. It's minus 40 is the correct temperature. And but some people, they just remembered it and wrote minus 40. But if they don't show the work, then I can't give them full credit. And so over the summer, some people wrote down minus 40 because they just remembered it and did it in class. I need to see the work for full credit. 49, I'll give you a hint. Use dimensional analysis. Same thing with 50. Try dimensional analysis. Those are the techniques. Give those a shot first.
Maybe just add another one.
You'll be given at least, I think, 2 hours for this. Let me know how long it took you to take this. What would be good is to treat this like a regular exam and see how much you can do on your own. And then for the ones that you can't do on your own, look those up. Let's see. If they still don't make sense, then ask me for some hints or something. Give me some hints.
He sent this page out through Piazza, correct?
Yeah. Two-page test. This one, like number 33. 33 is actually in another chapter, not chapters 1 through 5. 33 you don't have to worry about. Even though we did talk about percentages, you probably can figure it out based on percentages, but this one's really discussed in detail later on. $34 is a trick question. 34, I talked about it in over the summer in detail. For our class, I didn't talk about this yet. But 34 is a trick question. But maybe you can figure it out. Yeah. That's it. Yes. Yeah, you're right. Did you catch that? Because it's Cl2. When chlorine occurs in a compound, does it occur as the element chlorine? No, that's a trick. It's like, this would be like saying if you had 100 grams of table salt, in every 100 grams of table salt, you'd have 7 grams of Cl2, chlorine gas. When you eat table salt, do you taste any chlorine gas in there? No. Well, anyway, I want to make this a real kind of test, so why don't you try before I go through the answers. You can find that on Piazza. It's called Old Exam. Okay, any other questions? Okay, we're going to start chapter 5 today. Deals with atoms. So if we have a hydrogen atom here, and the helium atom is smaller. Well, one obvious difference is the size. The size of the atoms are different. Helium is a smaller atom. But in addition to the size, the weight is going to be different. The helium atom weighs a different amount than a hydrogen atom. But one thing that's tricky is that hydrogen atoms don't all weigh the same amount. You know, most of them will weigh a certain amount, but others will weigh a little bit more. There's some heavy hydrogen atoms out there, heavier hydrogen atoms. They're still really light. Atoms are light. And so, well, not only do they weigh different amounts, hydrogen has totally different properties than helium. And so, in trying to understand the properties, we're going to investigate the composition and structure of the atom in more detail. And so this is atoms. This is part one. And then we're going to look at other parts of the structure of atoms later in part two. But for atoms part one, what do we want to know? Well, the composition of the hydrogen atom. All right, so when we look at the composition, it turns out that most hydrogen atoms are going to have this. Most hydrogen atoms are what we call H1 or hydrogen 1. H1, when we look at it, it has one proton and one electron. That's it, just a proton and an electron. But there are some other hydrogen atoms that are present that aren't as common. So this one is the most common one, hydrogen 1. In fact, greater than 99.9% of all the hydrogen atoms are going to be this, that are found in nature. And so when you have a glass of water, you're drinking mostly H1 atoms, H2O molecules. Okay, then we have another one, it's hydrogen 2. Hydrogen 2 is known as deuterium. In fact, deuterium is more common than hydrogen 2 when referring to this. The only difference between hydrogen 1 and hydrogen 2 is compositionally. Hydrogen 2 has one proton, one neutron, and one electron. And then we have one more. Okay, this one isn't very common, it's less than 0.1%. But this one is extremely rare. This is hydrogen 3 or tritium. Only for hydrogen do they have special names for these. Do you know what we call these? Like hydrogen 1 and hydrogen 2? Isotopes. Isotopes are the same element, but different masses. And so this will be hydrogen 3. Hydrogen 3 will have one proton, two neutrons, and one electron. And so these weigh different amounts. They weigh different amounts. Well, how much does a proton weigh? And so let's look at some masses here. When we look at the mass, the proton weighs about 1 U. And so what is a U? A U is atomic mass unit. The atomic mass unit is more precisely known to a lot of sig figs. You know, we have the mass in U to a lot of sig figs, but you don't have to remember all those sig figs. You just know it weighs about 1 U. If you want a more precise mass, then you just look it up. A neutron weighs about 1 U. An electron weighs about 0.005 U. An electron weighs like 2,000 times less, roughly. And so the neutron and the proton weigh quite a lot. They're about the same, although one weighs more than the other. You don't have to worry about which one weighs more than the other. The electron's quite light. And so this has one proton. The electron's mass is somewhat negligible, so a lot of people ignore it. And so this weighs about 1 U. Now this one has one proton, one neutron, and an electron. The electron's going to add a little bit, but not much. And so the proton and neutron is going to add up to about 2 U. And so hydrogen 2 weighs about 2 U. And then hydrogen 3 weighs about 3 U. And so we have three different, hydrogen 3 is 3 times as heavy as a hydrogen 1. But the interesting thing about these isotopes, these are isotopes. Isotopes are atoms of the same element, but with different masses. The same element, but different masses. The interesting thing about these three isotopes is, yeah, they weigh different amounts, but they are the same element. Now, what does it mean to be the same element? What it means is that all three of these are going to have the properties of hydrogen. And so an example of that would be this. Even though tritium, you probably didn't drink any tritium this morning, but you did definitely drink some deuterium if you had a glass of water. If you had a glass of water this morning, then could you taste the deuterium? Does the deuterium taste any different than regular water? You would think so, but it doesn't. Does the deuterated water, we call it deuterated water, there's deuterium in the water. Does the deuterated water taste any different? It doesn't. In fact, it's going to have the same taste and the same chemical properties. The only thing that's different is its physical properties. It's just going to weigh more. That's it. And so they're the same element. That is, they behave the same, chemically. Physically, that's slightly different. Tritium is unusual, though. Tritium is special because tritium is radioactive. And so you don't want to drink much tritium in your water, and you didn't. You drank mostly H1 and a little bit of H2. H3, radioactive. You know what it means to be radioactive? What it means to be radioactive is it means the atom is unstable. And there's certain reasons why the atom becomes unstable, but the atom becomes unstable and it tends to decompose or break apart by radioactive processes, radioactive reactions. Now, radioactive atoms, these are important in chemistry, but these are not what chemists study. Radioactive elements and what we call nuclear reactions are different than chemical reactions and chemical properties. For chemists, we just study electrical interactions. Nuclear chemists, they study something a little different. And so we aren't really going to be concerned with the radioactive elements necessarily. We're going to focus on just these here. That's because the rules that govern nuclear reactions are different than the rules that govern chemical reactions. The rules that govern chemical reactions is just quantum mechanics and electrical forces, Coulomb's law. For nuclear reactions, we're looking at something else. Well, anyway, going back to this, you couldn't taste the difference here. In fact, even though it should be the same, and we drink deuterated water all the time, I bought a bottle of deuterated water. I needed deuterated water for an experiment I was doing. And so I had about 150 milliliters of pure deuterated water. The pure deuterated water looks like this. Each of the hydrogens is H2. The oxygen can be 16, 17, or 18. Those are the common isotopes for oxygen. So the oxygens were mixed up depending on. The oxygen 16 is the most common. And then a little bit of 17, a little bit of 18. And that I'll talk about later. And then H2. So this is deuterated water. I was tempted to taste it, but I didn't taste it. It should be the same. But it's more dense.
Coffee.
What's that?
Shouldn't be your coffee.
Maybe it's toxic.
Doesn't mean you shouldn't meet your coffee with it.
Yeah, it would be very expensive coffee. This stuff was very expensive. What they had to do is they had to separate. They got water; it's all mixed up. How do you separate it? It's tough to separate. One way that these are separated is by what's called natural fractionation processes. Did I talk about ozone? Ozone, yeah. Talk about it. Not all oxygens weigh the same amount. There's oxygen 16. Oxygen 16 has 8 protons, 8 neutrons, and 8 electrons. So oxygen 17 has 8 protons, 9 neutrons, and 8 electrons. Oxygen 18 has 8 protons, 10 neutrons, and 8 electrons. And so the only difference is, oxygen 18 weighs a little bit more than oxygen 16. When you breathe in oxygen, can you tell the difference? I guess if it were pure, you might be able to tell the difference. But what happens is this. ozone consists of 3 oxygens. And so you could have 3 oxygen 16s, right? Oxygen 16 is most common, so we could have 3 oxygen 16s. Or there's a chance that you're going to have 3 oxygen 18s. If you have 3 oxygen 18s, then that ozone weighs a lot more than an ozone with 3 oxygen 16s. And so one way you can tell the difference, ozone's produced, we have the ozone layer naturally, right? And then ozone is a part of smog. Ozone forms at ground level. Well, the ground level ozone differs compositionally from the ozone in the ozone layer. The ozone in the ozone layer has much more oxygen 16 and fewer oxygen 17 and oxygen 18, as you'd expect, because oxygen 17s and 18s are heavier, so those are going to sink more. And the ozone that's produced at ground level is going to have normal distribution. And so in other words, only the lighter oxygens will escape, Earth's gravitational pull and then rise up into high up into the atmosphere. But I was thinking the same thing. I was thinking, one way you might be able to separate the water is like on the surface of the ocean versus at the bottom of one of those deep trenches. I would think at the bottom of the deep trenches, you'd have heavier water molecules. More water molecules with deuterium H2 and more water molecules with 17 and 18. And that's a topic that's very popular with geologists. This is called isotopic fractionation. Isotopic fractionation is how the fractionates due to gravitational forces. The heavier ones sink more than the lighter ones. That's it. And so maybe that's one way. So if you take, I was curious, would the water taste different than at the surface? And my idea is no. I mean, chemically they're the same. So there's something that's dictating the chemical properties, and the chemical properties is not due to the weight. Even though this is radioactive, tritium behaves just like any other hydrogen. And so when you look at the chemical reactions of tritium, they're exactly the same as the chemical reactions of deuterium, which are exactly the same as the chemical reactions of H1. What's different is this atom's unstable and breaks apart. But before it breaks apart, it will react just like these will react. Right? Now, so it's not the weight necessarily that dictates, but what do all these have in common? They all have 1 proton. So this is something that's critical here, that 1 proton. What do all the oxygens have in common? 8 protons. And so it looks like the chemical properties of this are dictated not by how heavy it is, but by how many protons there are. And so helium is going to have different chemical properties. For sure, helium has some very different chemical properties than hydrogen. Well, one of the things is, helium is going to weigh more because helium is going to have, the most common form of helium is going to have 2 protons, 2 neutrons, and 2 electrons. Each proton weighs about 1, each neutron weighs about 1, and the electron's mass is kind of small, so we could ignore it. And so this one would weigh about 4 compared to the hydrogen. So helium weighs more, but there has to be something more to it. Well, yeah, there is. It has a different number of protons. Now, how does the number of protons impact its chemical behavior? Well, that's something we need to figure out as we go along. But right now, we're just taking random observations. These are just random observations and trying to piece together something. All right, so what we're going to look at first is this. Now, how did they figure out the composition of the atoms here? How was it determined? I mean, how did you know that hydrogen in 3 types of atoms that are found in nature? And helium. Helium actually has 2 types. But just observations and measurements and stuff like that. Well, we aren't going to get into that. Somebody determined what the composition of these atoms is. But what we're going to do is we're going to take a step back and then got to figure out how did they figure out what they're made out of, for one. And so let's talk about subatomic particles first. Subatomic particles is if you break atoms apart, they break up into smaller pieces. And so if I take a helium atom and break it apart into smaller pieces, I'm going to get protons, neutrons, and electrons. Those protons, neutrons, and electrons no longer behave like helium. And so the atom is the smallest piece that will retain its chemical and physical properties. But once we get into smaller pieces than that, we get protons, neutrons, electrons. Protons, neutrons, electrons, we can't differentiate between oxygen and helium or helium and hydrogen. There's no different. The protons are all the same, the neutrons are all the same, electrons are all the same. And so this is why the atom is the smallest piece of an element that you can have. Now the subatomic particles, we have the proton, we have the neutron, we have the electron. And so what we're going to do is we're not going to talk about the discovery of the proton, who discovered it, how it was determined. Nor are we going to talk about the discovery of the neutron. But we are going to focus a little bit of time talking about the discovery of the electron. And so the discovery, who discovered it, when, how, you can read if interested, read if interested. Our book doesn't get into it. The same thing with the neutron, read if interested. But the electron, you have to know. The discovery of the electron. The discovery of the electron is credited to J.J. Thomson. Actually, I don't think there's a P there, Thomson. J.J. Thomson in the 1800s. So he's the scientist who's credited for discovering the electron, although electrons been around longer than J.J. Thomson. And the instrument that he used is the CRT. Do you know what the CRT stands for? CRT stands for cathode ray tube. Cathode ray tube, the CRT. The cathode ray tube, if you look at old television sets, they operated using CRTs, cathode rays. And so what are cathode rays? It turns out cathode rays are beamed electrons, and cathode ray tubes are like lightning bulbs, but they're controlled lightning bulb. When you look at a regular lightning bulb, you'll see electrons, or see the effect of electrons. But if you can capture that and maintain it, you'll get a cathode ray tube. Now, how do you generate a lightning bolt or cathode rays? Cathode rays are going to be a little different than a lightning bolt, but what we need is we need two conductors, like two metals. So there's a piece of metal here, a piece of metal here. Now, one thing about metals is they conduct electricity. Electricity are electrons. They can conduct electrons. Now, if we have a power supply, what we can do is we can force electrons in one direction. So for example here, the power supply can pull electrons into it. And so what it's doing is it's sucking electrons out from the metal. Well, if it sucks electrons out from the metal, let's say we have a metal atom. Neither of these are metal atoms, but if we have a metal atom and we start removing electrons from that, there's going to be imbalance. We're going to be left with protons, and we have something like a charge imbalance. Right now the charges are balanced. I haven't talked about this yet, but protons are positively charged, so they have a charge of +1. Electrons have a -1 charge. And so what happens is the +1 charge of the protons balances out with the -1 charge of electrons. Neutrons are neutral, so those don't have any charge. To emphasize the charge, oftentimes people will write the proton abbreviation is P+, the neutron abbreviation is N0, and the electron is E-. Okay, we could do the same. But whether it's E- or E, both of these will have the charge -1. or N0 or N or P plus or P. All right, so what we have is something called electrical neutrality, but if we put a power supply here and the electrons are being forced into the power supply and forced out the opposite end, then what we're going to get is an imbalance of charge. In other words, as the electrons build up on this piece of metal here, it starts building up a negative charge. So we end up getting more and more negative charge because as we add more and more electrons here, it builds up. Over here, since we're taking electrons away, it's going to build up more and more positive charge here. And so in other words, this is like static electricity. Eventually you build up static electricity, and then, yeah, when you touch something, well, you're going to have an arc. Well, it's going to build up to a point where it can no longer sustain that. And so what's going to happen is the negative charge is going to build up, and the positive charge is going to build up. And eventually, as that negative and positive charge build up, we create what's called a higher potential or higher voltage. And when we hit about 1,000 volts or 2,000 volts or something, then we'll have an arc, which is a lightning bolt. Now, you'll have a little lightning bolt like when you discharge. You grab a piece of metal after walking across the carpet, you'll see a little lightning bolt. That lightning bolt is this discharge. That is, electrons are building up on this plate, and electrons are going to discharge over that plate there. All right, what we get is we get a lightning bolt if this discharge is taking place under normal atmospheric pressure, because the lightning bolt is the electricity has to travel through the air. And as it travels through the air, there's going to be collisions and whatnot. And so it's not going to be a straight path here. It'll be more of a random path as electricity travels across the gap here. But in a cathode ray tube, what we can do is this. If we can seal these pieces of metal in glass like this or a container and then evacuate it, and so we'll create a vacuum here. When we have a vacuum here, what that means is that we have a low pressure gas. We don't have as much gas. And it depends on how much we lower. If we can lower it to about 1/10 atmospheric pressure or less, like let's say 1 psi or something like that, then rather than having this random lightning bolt, we have a very nice beam that goes straight across, just a straight bolt of electricity going across. Like that. And so this is a method used to generate electrons. We can generate electrons by cranking up the voltage here. That's it. Making a little discharge, either a lightning bolt or a nice beam. When we have a nice beam, we call it a cathode ray rather than a lightning bolt. So this is a cathode ray, which is a beam of electrons. All right, so the electrons must have originated over here. The power supply is pushing the electrons over here. So electrons must be originating, actually maybe originating here, and then being pushed over here, and then finally going back over here. So cathode ray equals beam of electrons. Now, we know that metals are good conductors of electricity, but where does this lead to the discovery of electrons in all atoms? Because, for example, helium is not a great electrical conductor, nor is hydrogen, nor is any of these. And so there are different things that led people to believe that electrons are a fundamental part of all atoms. And one of the things that led them to believe is this. They changed the metal. So, for example, if they used aluminum here, they could try iron or platinum. Or it didn't matter what metal they used, they always got the same cathode ray beam. And so that meant, aluminum, iron, platinum all contain electrons. Okay, and then the gas that's in here, it's actually a bit more complex than I'm making it out to be, because the gas turns into plasma. Plasmas are partially ionized gases. And so the gas, they could change the gas in here. For example, they could use neon gas, nitrogen gas, oxygen gas. You change the gases in here and you still generate the same cathode rays. And so based on those, they inferred that electrons are part of all atoms. So that's inferred that electrons are part of all atoms. Now, we used to have a cathode ray tube that's broken. Now, what happened was that the glass got cracked here and some air leaked in and ruined the vacuum. So we don't get a nice smooth cathode ray anymore. So let me just show a video on cathode ray tube. How different is it from what? A light bulb?
Oh, yeah.
Well, it depends on what type of light bulb you're talking about. Well, incandescent light bulbs are different, quite a bit different. Incandescent light bulb, it's electrons doing the work there. But in an incandescent light bulb, you have like a tungsten filament.
Oh, yeah,
And then as the electrons, because again you need a power source pushing electrons through. So electrons get pushed through, it generates heat. And that heat causes excitation. And so this is different than an incandescent light bulb, but this is similar to a fluorescent light bulb. A fluorescent light bulb is like a cathode ray tube. So we could see one here, but you don't see the beam. If you remove there's a phosphorescent coating on the inside. If you remove that, you can see the beam electrons. Let's take a look. Yeah, just close the page. This was a pretty interesting one because there's a homemade cathode ray tube that this guy made. And so it's pretty interesting. Let me look at a part one of this. And on part two. I thought this is pretty cool. You could do something like this.
Hey guys, this Hey guys, this is Google King Science, and today I'm going to be showing you my homemade cathode ray tube project. This video will be split into two parts. The second part will go over the more technical aspects of the cathode ray tube and why it does certain things. The vacuum pump I'm using here is made out of an old refrigerator compressor. The power supply is made using a variac and an oil burner ignition transformer. A variac, also known as an auto transformer, allows you to vary the voltage coming from a wall outlet without altering the waveform. The output of the variac goes directly into the oil burner ignition transformer. Normally, an oil burner ignition transformer takes in 120 volts AC and steps it up to about 10,000 volts AC to 23 milliamps. But when I vary the voltage coming into it, I can either lower or raise the voltage coming out. The actual cathode ray tube was built using a wine bottle and some stainless steel wire. I drilled a hole into the side of the glass bottle carefully using a glass drill bit and inserted a wire bent in a half circle shape. Then I secured it with hot glue to make sure it was vacuum proof. As you can see, I made two of them, and they each have the wire at different lengths down the tube. To create a vacuum inside of the wine bottle, I just attached a hose bar into the vacuum hose and slipped a rubber O-ring over it. When the vacuum is pulled, the rubber O-ring sucks down onto the bottle and it just seals itself. This way there is no epoxy or glues needed. Now it's time to power up the cathode ray tube. To do this, we need to attach some electrodes to the terminals of the oil burner ignition transformer. Next, we simply attach one of the other ends to an exposed piece of the hose bar and the other to that wire we added into the wine bottle. Now I turn on the variac and slowly and carefully turn up the voltage. As you can see, a beam of electrons, also known as a cathode ray, appears. It glows a bright purple color in my case, due to small amounts of nitrogen and oxygen that are still left in the tube. Now, that time I was just running the tube on an AC current, so this time I'm going to add in a high voltage diode to make it a half-wave rectified current and see the difference in the beam. Now that we have that diode, let's power it up. As you can see, part of the beam that is glowing is only on one side of the tube. Last time it was on both sides, and there was a dark space in the middle. Now I'm going to demonstrate the magnetic deflection property of a cathode ray tube. Since it is a beam of electrons, it can be influenced by a magnet since electrons have a negative charge. Here I have a few magnets, and one side is marked with tape. When I put one side of the magnet that is marked up to the beam, it bends around it to the right. When I put the unmarked side to it, it bends around it to the left. Now I'm going to switch around the electrodes so that the electricity is flowing the opposite way. Now this time the dark space is on the other side. And when I hold up the marked side, now it bends around it to the left, and the unmarked side bends around it to the right. So depending on which way the electrons are flowing, they take a certain path around the magnet. Now I took out the diode and I'll show you the deflection of the beam when it's running on an AC current. As you can see, the beam appears to split around the magnet. Now, I told you earlier in the video that this is going to be split into two parts. The second part is going to go over the more technical aspects, describing why the beam splits and why it switches directions, if you're interested in that. I'll be using slow motion to analyze the cathode ray tube, and I'll show you some scientific formulas that explain some of the things that happen.
All right, so there was a bit of curve in that. I mean, if you could get better vacuum that is lower pressure, there's even fewer atoms in here, fewer molecules in here, so it'd be a more straight path in there. But that's essentially it for the cathode ray tube. The discovery of the electrons. All right, something that we'll talk about, but you don't have to know, is this. Now, how do you weigh an electron? You know, for example, the electron weighs about 0.005 U, atomic mass units. And then, how do you weigh an electron?
You shoot that beam through like a little piece of gold or something like that.
Shoot the beam through a little piece of gold? Yeah, that's good. You remember something about gold, a gold foil? That was something a little different. They didn't shoot electrons through a gold foil. That was the Rutherford gold foil experiment. This will be the J.J. Thomson CRT experiment. And so, do you know how they measured the mass of an electron? Well, one is, what is a U? Do you know what a U is? You heard U's before? Atomic mass units?
Yeah.
Well, what is the definition of a U? You know, for example, a kilogram, they're somewhere locked in some safe in France is the standard kilogram. You know, this is as close to 1 kilogram as you're going to get. But they also have one in the NIST building in Washington, D.C. And so there's an object out there that weighs a kilogram, and you can compare your kilogram to their kilogram to see how close you are. But what is a U? You know what a U is? A U is this. So let's talk about atomic mass units, and then let's talk about weighing things next. Then we'll talk about weighing electrons. So the atomic mass unit, these are units that are convenient for weighing atoms, extremely small masses. And it turns out the definition of the atomic mass unit is given by this. If we have one carbon-12 atom, so this is how we write it. If you look at carbon-12, well, carbon-12 has 6 protons, 6 neutrons, and 6 electrons. That's the composition of that. One carbon-12 atom is defined to weigh exactly 12 U. Exactly 12 U. So that 1 U is 1/12 of a carbon-12 atom, but can you get 1/12 of a carbon-12 atom? Is it possible to split it? No. And so usually we'll just think of it like this. It weighs 12 U exactly. Now, is there a way to weigh it? You know, because now we would do this. If you had a kilogram balance, you know what you need to do? If you had a kilogram balance, you need to go to France or Washington, D.C., and you need to get that kilogram weight and then put it on your balance and make sure it's reading 1 kilogram. You know, you want it reading 1 kilogram exactly, even though this is exactly what you get. If it's not reading 1 kilogram, then what you do is you calibrate it. It's like, you know, old scales. Have you ever seen the old spring scales? They have a little dial, and you calibrate it using the dial, so you just make sure it's reading 0. Well, if you had a kilogram weight, you put the kilogram weight there, and then you just rotate the dial until it's reading exactly 1 kilogram, right? That's called calibration. And so we do the same thing. We calibrate it. But for something like this, now, how do we weigh a single atom? You know, can we put a single atom on a balance? I know a single carbon-12 atom is going to weigh exactly 12 U by definition. Although, let me backtrack a little bit, because it used to not be defined this way. This is called an arbitrary definition. Why carbon-12? Why carbon-12? Why not oxygen-16? So does somebody have an answer? Why not oxygen-16? Well, one, oxygen-16 weighs more, but that's okay. If oxygen-16 weighs more, then maybe we'll just call one oxygen-16 atom. Rather than 12U, we'll call it 16U. Well, why? Because the carbon-12 people went out over the oxygen-16 people. The oxygen-16 people were okay up until the 1950s and 1960s. Up until, I think it was late 1950s, all balances, you know, these are balances that weigh out electrons. And these balances, they don't call them balances, but we'll talk about what they're called in a minute. But these balances that weigh out single atoms, you know, all of them were calibrated using oxygen-16. So if you have an oxygen-16 atom, you post the oxygen-16 atom on the balance and make sure it's set to 16U. And then the carbon-12 people came along, and the carbon-12 people said, no, let's switch over to carbon-12. And they did. Everybody switched over to carbon-12. Now you put a carbon-12 atom on the balance, and you make sure it's reading exactly 12U. So you just punch it in. It's reading 12U, it's calibrated, it's good to go, right? But what does that mean? That means that all the masses, the mass of the electron, the mass of the proton, mass of the neutron, all those masses are different if you look in an old table than a new table. And so when you compare the masses of the atoms, you're looking at an old table, don't don't bother because they're all referenced to oxygen 16, not carbon 12. Now, why carbon 12? The reason for this, I think, is because of the development of lasers. You know, oxygen 16 used to be the standard because when you weigh these things, you have to weigh them in gaseous form. And we'll talk about how you weigh gaseous atoms in just a minute, but they have to be in gaseous form. Well, carbon is not gaseous. Carbon's either going to be in graphite, diamond, or buckyballs. And so it's inconvenient. But then gases are a hassle because gases aren't very concentrated. Gases consist mostly of empty space. And so you got to buy a lot of gas to get a few atoms, right? Versus if you buy some graphite, you get a lot of atoms in a very small package. And so working with gases is a hassle. So I understand why people wanted to switch from oxygen 16 to carbon 12. The problem is in order to weigh carbon 12 atoms, you have to vaporize them. Well, it's very difficult to vaporize diamonds, very difficult to vaporize graphite. You know, both are incredibly tough to vaporize. But with the advent of lasers, you know, they could shoot lasers at the surface and vaporize atoms off the surface, and then weigh those individual atoms. Now, what instrument do they use to weigh them? Well, we don't call them balances. We call them mass spectrometer. And so let's take a look at mass spectrometer in action here. Just the first part of this video.
We can begin with a simple analogy to get across the most basic principle of the mass spectrometer.
Wait. Back up.
We can begin with a simple analogy to get across the most basic principle of the mass spectrometer. 3 balls of equal size with different mass. The lightest, the ping pong ball, straight down and straight through. Somewhat heavier, golf ball, straight down and straight through. And the heaviest, the snooker ball, straight down and straight through. A hairdryer would be put on at this point, blowing air from right to left. Look at the deflection of each ball. 5 for the lightest, the table tennis ball, 3 for the golf ball. And what about the heaviest? Snooker ball has the least deflection, score of just 1. Conclusion then is the ball with the greatest mass is deflected the least. In the mass spectrometer, a magnet plays the role of the blow dryer. Look at the labels: a heater element to create a vapor, an ion accelerating field which gets the positive ions streaming from left to right towards the magnetic field, the detection plate at the top right there. The entire mass spectrometer is enclosed and is evacuated. There are no air particles inside so that the beam of ions has a free run. No air particles to strike. In the copper color you see 2 rectangles. One at the bottom is the electron gun. It's an element which is heated and generates electrons which are attracted towards the capture plate, the larger of the copper colored rectangles. This produces a beam of fast moving electrons. Entering at the bottom left there you see the sample represented with green spheres. If it's not already a vapor, your sample will have to be heated to create a vapor. We'll have, our sample might be ions, atoms or molecules. If it is atoms or molecules, we have to change the atoms or molecules into ions. This is the role of the electron gun. The electrons will knock off 1 or more electrons from the atom or molecule. When an atom or molecule loses an electron, it doesn't affect its mass, as electrons have negligible mass, but it will create.
So an electron gun is similar to the CRT here, the cathode ray. You just generate the voltage, is one way of doing it, and then electrons shoot across. And these electrons, if they strike the atoms, they can create a charge on the atoms. You need a charge on the atoms because what you're going to do is you're going to shoot the atoms through here. They get accelerated because of the attraction. It depends if these are positive, these are negative, so we can accelerate or these negative. You accelerate through here and then pass by a magnet. When you have charged particles pass by a magnet, they get deflected, like the electrons in the cathode ray tube got deflected with a magnet. Same thing happens with atoms. So this operates the same as a cathode ray tube, except that we're not shooting electrons, we're shooting atoms, charged atoms through there.
A particle which is a positive charge, or two positive, it loses two electrons. Adjacent to this field is a positive plate. And the moment positive ions are produced, the positive plate will repel them from left to right towards these blue spheres, which represent plates with slits in them. And the role of the slits is to focus the beam. Watch now as the green spheres turn to red, brown, or yellow, creating ions of a different mass to charge ratio. You'll see the yellow spheres represent the ions with the greatest mass to charge. They're deflected the least, whereas the brown, they're deflected the most. They're the ions with the lowest mass to charge ratio. As they reach the detection plate, they create a small electric current which is amplified, and this produces the stick diagram that you see in the spectrum on the top right. The more ions of a particular mass to charge ratio, the greater the current, and the taller the stick of the spectrum.
All right, so basically what he's saying is the heavier atoms are going to be less deflected by the magnetic field, and so they'll go more straight. So these would be the heavier ones. They strike at the plate. This is the detector plate. They strike the plate up here. Whereas the lighter ones are going to be more deflected. So the lighter ones are easily, they can change the path much more easily. They have less inertia, and so they can hit over here. And so here we can just see, based on how many strikes we have, three different masses. This would be the heaviest atom, this would be the lightest atom. This is called a spectrum or mass spectrum. It just shows us the range and height of atoms that we have. So the mass spectrum, that's going to come from the mass spectrometer. Your book doesn't have a figure of the mass spectrometer, but it does have a mass spectrum in there. So let's take a look at the mass spectrum in your book here. This is a figure 512. And so what we're looking at is we're looking at the strikes, where it's hitting the detector. And so we have an atom that weighs around 22U and an atom that weighs around 20U. It looks like the one that weighs around 20U is much more, the peak is much larger. And the peak is much larger because we got a lot more atoms hitting there than over here. So this is more common, these are more rare over here. And so we look at the 22, it's less deflected, the 20 is going to be more deflected. If we were looking at electrons, the electron is rapidly deflected over here. And so we have these strikes at different places, but how do we know our balance is reading correctly? That is, how do we know that these numbers are correct? These numbers, this is just around 20, and then we can weigh it to a high degree of precision. The way we know that is we first calibrate this. When we first calibrate this, we have to run carbon-12 through this. When we run carbon-12 through this, it's going to strike somewhere. Where it strikes, we set that equal to exactly 12U. And then we can record these other masses. And we could generate a table like this. This is called the table of isotopes. Here. So, actually 338. Right in just a second. So what we do is we run carbon-12 through. We know that that's defined exactly as 12U, and then calibrate our scale. Once we calibrate our scale, then we can weigh everything else relative to where it strikes. So for example, beryllium's a lighter one, so it's going to strike, it's going to be more deflected. We can use some physics to calculate, based on the angle of deflection, how much it weighs. Carbon-13, which has one extra neutron, over carbon-12 weighs a little bit more, so it strikes the detector a little bit farther down. And so based on the strike position, we can weigh these with a high degree of precision. I mean, take a look at how many sig figs there are. Huge number. Okay, we're going to come back to this after the break. Let's take a break right now, and then we'll start again.